Next up is simple harmonic motion. Now, you'll note in the way that I've laid this out that this comes along with circular motion. And that's because simple harmonic motion and circular motion have got an awful lot of things in common. So it makes sense to do them together and think about them together. So, first of all, I just want to define what I mean by an oscillation. Because this is actually quite an important thing, particularly when it comes to talking about practicals. I imagine that you know the questions they ask when they ask you to describe how you might do a practical. Simple harmonic motion might be one that they ask you about because it's got some very clear rules about things you need to watch for, things you need to be careful about, and how you do these. So it wouldn't surprise me if this was the practical exam question. So let's make sure we've got this all really clear in our heads. So an oscillation is just a repeated motion around a fixed point. That fixed point is what we would refer to as the equilibrium position. So it's the point where the object would return to once the oscillation stops. So you can think of it as its rest position. So if I've got a pendulum like this here, when it's just hanging straight down, that would be its equilibrium position. So we know we have our pendulums swing side to side. We'll talk about those a lot. We'll also talk about masses on springs. So if this was a spring and this was the mass, this would be the rest position, and I could pull it down and it would bounce up and down, and it would be oscillating around this equilibrium position. Excuse me. So just as we have time periods for our circular motion, so the time it takes for the object to go all the way around the circle, we have a time period for our oscillation. So it's the time for the object to complete one complete oscillation. And you've got to think a little harder about these ones, because with the circle it's easy. It's done when it's back where it started from. With the oscillation, that's not quite true, because when the time is 0, it's going to be in the equilibrium position. And it's then going to move away from the equilibrium position. Once it's a quarter of the way through its time period, it will be at its maximum amplitude, the furthest away to one side. It's then going to move back towards the equilibrium position. It will hit the equilibrium position again at half of the time period, but then it will continue moving the other way. Once we're 3/4 of the way through the time period, we're now at our amplitude in the maximum amplitude in the opposite direction. It's then going to move back to the equilibrium position, and that's now when it's one time period. So it's kind of like it's done a circle, but you've got to remember that it's going to pass through the equilibrium position and back again. Often, when you're doing a practical, because you have this issue of it passing through the equilibrium position twice, it can lead to mistakes when it comes to counting how many complete oscillations have been done. So to prevent that, what we often do is start counting from a maximum amplitude, because the time period will be, for this point, the time it takes for it to go and come back to this point. So you often make fewer mistakes with your counting if you count from the maximum amplitude rather than from the equilibrium position. So talking of the amplitude, let's just have a little talk about how we define that compared to the displacement. So we would say that when the object is at its equilibrium position, that the displacement is equal to 0. And when it's at its maximum amplitude is when we would have our maximum amplitude. So my maximum displacement, sorry. So when it's at its amplitude, I have its maximum displacement. In this case, I'm going to say it's in the positive direction, and it's going to have that same size amplitude. Has to press the right direction. Same size amplitude, just in the opposite direction on the other side. So in this case, I'd say that the displacement is equal to minus the amplitude. Okay, and then it goes back to it as being 0. So just a little bit of terminology, make sure you've got a head round, remembering difference between displacement and amplitude. This should be ringing some bells from when we did waves, because again, there's a lot of crossover. Talking about crossover, frequency. It's measured in hertz. It's equal to the number of complete oscillations per second, and hopefully remember that frequency is equal to 1 over the time period. So again, things that we have done at AS that come back, that feed back in. So all that wave stuff that we did, you're going to want to start reviewing that as well. Okay, so simple harmonic motion. Simple harmonic motion is a pattern of oscillations, and when the oscillations are all approximately the same, it's what we would call simple harmonic motion. So we're just doing the same thing over and over and over again. And some examples, told you before, we've got the mass on the end of the spring, pendulum or a swing, molecular oscillations, a ruler oscillating at the end of that bench, you know, that obnoxious thing where you stick up the bench and you go twang. Oscillations of guitar or violin strings, the tides as an approximation of SHM, even breathing is pretty close to simple harmonic motion. So simple harmonic motion is a very important thing, and it's a very common thing in nature, so it's something that we're going to study quite a lot. Okay, so I just want to show you what I mean when I said that circular motion is actually very similar to oscillations. So what I've got here is a little animation that shows a spring undergoing simple harmonic motion, and it's got a little green dot in its centre, and over here I've got that green dot undergoing circular motion. And if you look at the motion of the green dot in the circle compared to the motion of the green dot that's going up and down, you can see that there's a lot of similarities between them. Okay, so if I just pop some lines on, it might make it a little easier to see. So we could consider that the amplitude of the oscillation is equal to the radius of the circle. So if you look, that when they're both at the top, they're both at the top. When they're at the bottom, they're both at the bottom at the same time. They also both pass through the equilibrium position, which is the green line, at the same time. Now, importantly for my one doing SHM, you should be able to think about the way it's moving and realise that it's going to be moving its fastest when it goes through the equilibrium position. So that's something to bear in mind. And the last thing that we can say is that the time period of the oscillation is equal to the time taken for the object to complete the circular path. So it's kind of like I've just taken that circular motion and I've just squashed it flat. So I've taken out and just made it move in one plane, and then I see that dot just going up and down. And it would be exactly the same as my spring is doing. Okay, so hopefully we can see that there is a lot of crossover between circular motion and simple harmonic motion. Now, some more things that you are just going to have to learn and be able to regurgitate for those very easy marks in the exam. In this case, it's the conditions for SHM. So if an object is performing simple harmonic motion, we can say the following things. Its acceleration is proportional to its displacement from the equilibrium position. The acceleration is always directed towards the equilibrium position. So mathematically, I can say that A equals minus kx, where k is a constant. The minus sign indicates that the acceleration and the displacement are in opposite directions. So these are our two conditions for SHM. Sometimes they'll ask you for the conditions to do with the acceleration or something like that. But these are the things they want. Acceleration is proportional to displacement, and it's always directed towards the equilibrium position. Okay? So let's have a little look at how the acceleration does vary with SHM. Oh, sorry, 1 second. So I said that there was a constant, and this constant k is equal to 2 pi f squared or 2 pi over t squared. You will have one form of this in your data book, so this one, but they might not give you the frequency, they'll give you the time period. Now you can just convert before you put it into the equation, or you can just remember and change the equation. It doesn't matter, whichever you feel is the quickest or easiest for you. Actually, scratch that. I don't care which you find the quickest. I care which you will get right in the exam. So make sure you use the version you will get right. So if I just take that constant and pop it into a equals minus kx, it gives me a equals minus 2 pi f squared x, which is the version that's in your data book, or I could have that one there. Now if I just plot a graph of a against x, what we should find is that I get a graph that looks like this. So it will be a straight line, it will go through the origin. I will have it that it stops when I'm at my maximum acceleration, when displacement is equal to my maximum amplitude, apologies, not acceleration, amplitude, maximum amplitude, and that's going to be when my acceleration is equal to 2 pi f squared times x. Okay, so it makes a lovely straight line like this, and I can see my maximum amplitudes of it, and I can also get a value for my acceleration. And obviously we can see that when it is at the equilibrium position, the acceleration is equal to 0, and I have my maximum accelerations when I have my maximum amplitudes. And obviously that's all going to come down to, because of F equals ma, and to do with the size of the forces. Because obviously when it's in the equilibrium position, whether it's going to keep moving or not, when it's in the equilibrium position the forces should be balanced, so there should be no resultant force, so there should be no acceleration. When it's at its maximum amplitude, the forces will be the most unbalanced, so I'll get my biggest resultant force, so I'll get my biggest acceleration as well. Sorry about that, guys, still coughing a bit. Right, so if I then find the gradient of my line, it's going to be equal to minus 2 pi f squared, which should be pretty clear because it's a very simple straight line. Right then, let's have a little think about the displacements. So I've already said that the displacement is going to be x, and we might want to know where the object is displaced to at time t. So we can use an equation, and the equation we use is x equals a cos of 2 pi ft, and that's given to you in a data book. Obviously, if you haven't got f, you can use over the time period instead and just rearrange it. Again, you pick whichever works for you. And a here is your maximum amplitude. Just make it positive, that's fine. Just remember that if you end up with a negative displacement, it just means that it's in the opposite direction to whichever way you decided was positive. Because remember, minus signs tell us direction when we're dealing with displacements, because displacement is a vector quantity. Right, let's have a little look at these things changing. So what we've got here is an object that has a spring on either side of it, and it's undergoing simple harmonic motion. So when it's in the equilibrium position, both springs are in the relaxed position, and we can see that the force gets to 0. Further away it gets from the equilibrium position, the larger the force, and we can see that the force keeps changing direction. Now we can see that the force and the acceleration are clearly proportional to each other, as they should be, and they're in the same direction. So I have maximum acceleration at the amplitudes and 0 acceleration as it passes through the equilibrium position. The displacement is equal in magnitude but opposite to the direction of the acceleration, so we can see there's proportionality there, but the direction is opposite. The thing that looks very different is the velocity. So at our maximum amplitudes, you can see that the velocity drops to 0. So at both of the amplitudes, the velocity comes to 0, so it stops at either end, which makes sense because it's changing direction. And it has its maximum speed when it passes through the equilibrium position, which is again all to do with the forces and the fact that it's had the most acceleration applied on it for the longest time before the acceleration changes direction. So we're going to have our maximum speed in the middle and a speed of 0 at either end. I've got maximum acceleration at either end and 0 acceleration at the equilibrium position. Graphs of this will abound, so be prepared to draw lots showing what's going on. Yep, and that's where we're going to leave it for this. I would sit and probably watch this a little bit to make sure it goes really firmly into your head what's going on with the forces, the acceleration and the velocities. The equations, they look a little gross, but they're really easy to use. It's just plugging numbers in. You just got to learn the conditions and remember when we have our maximum amplitudes, what's happening, and when we're at the equilibrium position, what's happening. So it's just going to be a matter of learning the basic facts. And once you've got the facts down, this gets quite easy. Okay, so I will see you in class. If you have any questions, just remember to ask me.